Hello and welcome back. This is lesson 2.6 on linear regression. Today we're going to learn how to write a linear regression equation and use it to make predictions. We're also going to interpret the parameters of a linear regression model and then also know how to and understand the dangers of extrapolation. Okay, so let's do a quick recap of some vocabulary. Remember that an explanatory variable is the variable that most likely is causing the change in the other variable, and we typically call this the x variable on a scatter plot. And the response variable is the variable that is reacting or changing in response to the change in the other variable, and this is typically called our y variable on the scatter plot. Note that for bivariate data, which is data with two variables, usually numerical, it's not always obvious which variable is explanatory and which is response. So, for a given set of data, we can use linear regression to fit a specific equation of a line to a set of data. So we're going to, and then we can use that linear equation to make predictions for the response variable using a given value of the explanatory variable. All right, so we're going to look at an example that does the cardiovascular fitness versus athletic performance. So the question is cardiovascular fitness as measured by time to exhaustion running on a treadmill related to an athlete's performance in a 20-kilometer ski race? And so this is our data. And what do you think? Well, as you can see, it's decreasing. So the more time you spend on the treadmill, the less time you are on the ski time, going down the hill. Okay, so many times below is what we call a computer output of a linear regression analysis program. Many times in AP Stats, you're not necessarily, and it's not always true, but more times than not, you will get a linear regression analysis program that gives us the data we're not actually figuring out, but we're using this data to make our predictions and interpretations, okay? Let's start with the linear regression equation. Well, you all remember the days of y equals mx plus b when you're doing a linear regression back in Algebra 1 when you did it. In this case, when we're talking in terms of statistics, it's going to be y hat, and the reason it's a y hat is because we're predicting the y values, thus the hat over the y. And then, of course, b with the lowercase 1 is our slope. And in this case, it's x, but notice we don't have a bar over x, and that is because we're using actual values of x from our data. So there is no hat. It's not a predicted. And then, of course, b naught would be what we would refer to as the y-intercept. Okay, so what is our slope? Well, the slope, excuse me, the slope of the regression line tells us the predicted change in the y variable, our response variable, but for every 1 unit increase in the x variable, our explanatory variable, okay? So if you're asked to interpret this value, you would say something like, as x increases by 1 unit, the model predicts that y will increase or decrease by some units. Now, x in this case would be whatever our explanatory variable. You wouldn't necessarily say x, you would say whatever that explanatory variable is in context. You wouldn't necessarily use the word unit. You would use whatever unit they would be giving you. You have to say model predicts, because remember, that's what the y represents. And then the y, of course, is whatever that response variable is. And then, of course, increase or decrease will depend upon whether it's positive or negative. And then you'll have some value. And then, of course, you have to include the units, okay? So the y-intercept is of the regression line tells us where the predicted value for the y variable when the x variable is equal to 0. And please note that this may or may not have a meaningful significance in a situation. And you'll see as we go along some examples when you talk about where the x variable is 0 and the y variable, y-intercept they have absolutely makes no sense. Okay, and it's important to say it does not have a meaningful significance in the situation. Okay, so if you're asked to interpret this value, you can say something like, now once again, the x and the y and the unit are just, you fill those in with the correct verbiage from or in context to the problem. So when x is equal to 0 units, the model predicts, notice you keep seeing that, model predicts that y will be whatever units. Okay, so I'm fine right here. So let's use our linear regression data. And this is on, remember, it's the treadmill time on the treadmill versus ski time. Okay, so what is the linear regression in context? Now remember, the model is predicting ski time, so it's going to be predicted ski time. So you have the little hat over it. If you don't want to put the little hat, you can also say predicted ski time is equal to, and what is our slope? Well, notice the coefficient under the predictor where it says treadmill, that coefficient would be our slope. So it's going to be negative 2.3355. And now remember, with slope comes our x variable or explanatory. And in this case, it's going to be treadmill time. You wouldn't put x there. You would just put in parentheses treadmill time. Okay. And then, of course, we have a y-intercept, which is the coefficient under our predictor or our constant. So it's plus 88.796. I do want to caution that when we're giving you a data set like here, you don't round the numbers, okay? You give the numbers as they are given, okay? So now let's interpret the slope, okay? So remember, as the treadmill time, because that's what we're talking about, as the athlete's time running on a treadmill increases by 1 minute, that's the 1 unit, the model predicts that their ski time will decrease by 2.3355 minutes, okay? I'm using what I had told you in the previous slide. I'm just putting in the correct words, okay? So now let's interpret the y-intercept in context. And is the y-intercept meaningful in this situation? Okay, so for an athlete whose running time on the treadmill is 0 minutes, the model predicts that their ski time will be 88.796 minutes. And does this have meaning? Yeah, that's probably meaningful in this situation, because it's basically saying if you don't do any time on the treadmill, this is how long it's going to take you to be on the ski, how much ski time you'll have. So identify, interpret that correlation coefficient. Well, it says right there, it says r dash squared. So r squared is 63.04%. Remember, you have to change it to a decimal, and then you take the square root, and then of course you take the square root and it's plus or minus. Now remember, it is going to be direction, and since our slope is negative, that means that r is going to be negative. So we know it's going to be negative 0.79. Now, what does interpret this r square value for this regression in context? I'm sorry, interpreting the correlation coefficient. I'm sorry, going ahead of myself here. The correlation coefficient, negative 0.79, indicates a linear relationship between treadmill time and ski time. It's important that you say linear relationship between treadmill time and ski time, and tell me what relationship we're talking about that is moderately strong and negative, okay? So you put it in context. You tell me that it's linear or nonlinear. You have to do that. So you tell me whether it's linear or nonlinear. You put it in context, and then you tell me strength and direction, okay? So now let's interpret the r square value for this regression in context, okay? Now remember, R square is 63.04%. So basically it says about 63.04% of the variability in ski time can be explained by the linear model for treadmill time versus ski time. Okay. I have to tell me what's the variability. What is it that it's explaining? It's the variability of ski time, which is explained by the linear model. And I include what the linear model represents in context, treadmill time versus ski time. Okay, so correlation coefficient R, all right? Now remember that the correlation coefficient is a measure of strength and direction of a linear association, okay? So, and basically it just tells us how accurate the predictions from the linear model will be. Now, if asked to interpret this value, you say the correlation coefficient indicates a linear association. That is, and when you say linear association, tell me what it is in context. That is, and once again, strength, strong, moderate, weak, and direction, positive or negative. Now, excuse me, put myself down here. We also have the coefficient of determination, which we call R square. Now, R square is another value that gives us an idea of how good the model is, okay, at predicting the Y values from the X values. And if you're asked to interpret, you basically say about whatever percent of the change in the Y can be explained by the linear model for X and Y. Make sure you're always putting it in context. You just don't say Y, X, and Y without putting it in context to the problem. Now, we have two measures of strength, and why not just stick with one or the other? Well, you have to remember that the correlation coefficient R only applies to linear models. And when statisticians have to use nonlinear models for a set of data, those other models also have an R square that is calculated. And so comparing the R square for different models tells us which model is the best fit. All right. So going back here, let's put this one making some predictions of some other things, some other examples here. Okay, excuse me. All right, so let's look at age in months versus height in centimeters. All right, I know you notice that it goes from 0 months up to, it looks like 33 months. Okay, and so the model, the predicted height is equal to 64.4 plus 0.631 times your age. And of course, it's your age in months and your height in centimeters. And so we can state that if we look at 18 months, that an 18-month-old is predicted to be about 75 centimeters tall, which is about 30 inches or 2.5 feet. Pretty reasonable. Also, a 30-month-old is predicted to be about 83 centimeters tall or 33 inches, all which are fairly reasonable. But let's go ahead and ask ourselves, what if you were an 18-year-old, which means you're 216 months old person? And if you use that model, it comes out to be about 79 inches or 6 feet 7 inches. Now, I'm not saying that an 18-year-old can't be 6 feet 7 inches, but that's more on the side of unusual than normal. Okay, so let's look a little bit. And if you look at the graph, notice how we had to pretty much condense the data that we had in order to get our piece of our 216 months, which is way out here. Let's look even further and let's look at a 40-year-old. If we look at a 40-year-old person, and I don't remember how it is, but here it is, it's almost like 500 months, okay? It's almost more than double, okay? And that says someone's going to be 12 feet tall inches, which 12 feet tall, okay, which we know is not reasonable. And so this is where we come up with what we call extrapolation. And extrapolation basically says when you go beyond the ends of our data, okay, our data only went up to a little over 30 months, All right. And as you can see, if you start going outside of that, it makes your predictions unreliable. All right. And we call that extrapolation. Okay. And we really shouldn't try to make predictions beyond the X values in our given data because this is called extrapolating. And extrapolation leads to predictions that are unreliable, like telling you someone at 40 years old they're going to be 12 feet tall, or 18, which once again, I'm not saying couldn't happen, but 18 being 6 feet 7 inches. Okay, so I just want to end this with reminding you not to forget that correlation does not imply causation. Noticing a relationship or even a correlation between two variables does not automatically mean that one variable is causing the effect of the other, or that changing one variable will automatically change the other. Okay, so that's all for today, and we'll see you next time. Bye-bye.